All right, hello, good noon. So this is our last lecture we're going to be doing before the um, Monday review day and then the Wednesday test. So today we're going to kind of finish up with inductors. Um, and then, yeah, that'll basically be it. But before we do that, I wanted to really just highlight, if you haven't already, my reminder to you all is that to prepare for the test, the best thing you can do is go through the problem set problems. So this means problem set solution. So problem set 1 and problem set 2. Problem set 1, it's specifically because we're covering DC circuits on this test. That is the two last sections of this. So the section on DC circuits and the section on um, current and resistance. And this may seem like a lot, but these questions, especially current and resistance, are very quick. So current and resistance, DC circuits, and then problem set 2 is everything except for the last piece of this. So if we look at this, everything in here, well, just sections 1 through 3, not inductance. Inductance is not on the test, but sections 1, 2, and 3 are. So please make certain that you are going through the problem set problems, because that is basically the best indicator of how you're going to do on the test. If you can go through these problems, if you know how to get the answer and you know why that is the right answer, if you know why you did the process you did, you're set. Just getting the right answer isn't enough. You need to understand how you're doing it to make certain you're actually prepared, and the quiz, reviewing the quiz questions as well. So those are the two main things. If you review those, you should be set. If you do not, that's pretty much usually the cases where I see students not doing well, is students that just reviewed the quizzes. Make certain you're reviewing these. And I'll send out an email again just reminding everyone, please be going through these. Make certain you're actually looking through these. And if you have any questions, let me know. I'm happy to help however I can. So the test has been made. I went ahead and so I've made all the problems with it. I went through them once. I had someone else go through to check the answers. It took me about 25 minutes to get through 25 problems, whereas I'm only giving you 20 problems. So you all should be have more than enough time for it. Please, during the test, make certain you go back and check your answers. You should have plenty of time to do that. But again, do not work with other people. That's the one thing you're not allowed to do. Okay. So that was just my quick. Please make sure you're putting in the effort and actually going through the problem set stuff as well. So last class we were talking about inductors, and so inductors, they're not on the test, but they will be on the final. So we're going through these now because we need to spend our time wisely. So we went through inductors, and basically the reminder, the big thing is things have an inductance, and this is a nature of a device to oppose a change in current. The quick example I gave was if you put a solenoid is kind of like that slinky in a circuit, and you went from no current to some current, that generates a magnetic field. The solenoid, remember from Faraday's law, opposes changes in magnetic field in it, opposes changes in flux. So the solenoid actually generates a current the other way. So normally we see in this problem, current would want to flow from the positive to the negative terminal, and the solenoid will actually make a current. It won't completely oppose it, but a current that will oppose it. So I draw two eyes here, one bigger eye induced. Make a current that opposes it. And this is the idea of inductance. It's opposing that change. The second it's like kind of constant, you're fine. And we did did that. Gave an example problem with finding the inductance if you have the EMF and the flux. Showed you some pictures of what inductors looked like. And then we also derived the inductance of a solenoid, which is these two equations here, mu naught n squared times the cross-sectional area over the length of it, or mu naught little n squared area times the length, where the little n is the number of turns per length. So that's kind of the big equation we're using. That's the inductance of a solenoid. And solenoids are pretty much the only devices we're really going to be caring about. So gave you all a couple of practice problems with these. We talked about that they store energy. So kind of like a capacitor stores energy, an inductor stores energy. Capacitors store that energy in an electric field. Inductors store it in a magnetic field. And the equation is this 1/2 the inductance, that's a capital L, times the current going through the inductor squared. Okay. So that was just a quick review of what we covered last time. So the question is, how does the energy of a solenoid depend on its geometry? Well, we just said that the energy equals 1/2 Li squared. And we know that the inductance of a solenoid equals mu naught capital N squared A over L. Remember, that was the one that I just quickly reviewed. Right here, the inductance of a solenoid, mu naught capital N squared cross-sectional area over L, where L is the length of it. Or I'll put both versions here. And so here's my solenoid. We imagine that's my cross-sectional area. And the length, I'm running out of room, so I'm going to need to move this down. And the length is here. And then it has N turns total. So how does the energy of a solenoid depend on its geometry? Well, the more turns I have, the more loops I have, and so it's going to oppose it stronger because you get more flux, more change in flux. Because remember, this whole inductance of a solenoid was based on how much flux kind of goes through it. So the more turns, the more energy you store. The bigger the cross-sectional area, the more energy you store. The longer the length, the less energy you store, and that's because it's going to be less, it's going to be kind of more spread out. The more compact it is, kind of the stronger field you're going to get inside that thing. So that's the gist of it. And it should make sense. The bigger the area, the more magnetic field lines are in there, the more number of turns. If each turn contributes to the flux a certain amount, if I have more of those, then I make more of a change in flux. And this whole idea of inductance is the bigger the change in flux, the more it's going to oppose it. So all that to say, the bigger you make this thing, for the most part, the more energy you store in it, with the exception of length. The more compact you make it, the better. So, and then I gave you all this quick question with it. That was one of the quicker questions last time. Okay, and this is what we're going to start moving into things that's basically going to cover the rest of this, which is what happens when we put a solenoid in a circuit. And I already talked about this a little bit, but let's consider that circuit I drew at the very beginning, where you have a switch. So you have a battery, a switch, and then this is a solenoid. This is the symbol for the solenoid. It's the loop. It looks like a solenoid. And the question is, basically, so a solenoid starts with 0 current through it, and then we push some current through it. It will oppose the change in current. Why does this happen? And this is what I talked at the very beginning, so it's just kind of rehashing that. The second that you close this, some current will start to try to flow through the circuit. And this current is going to go along this solenoid. And so if we kind of just look at this solenoid, it went from no current to some current. And if it went from no current to some current, that means we went from no magnetic field to some magnetic field. Well, Faraday's law says we want to oppose that. So it is going to induce a magnetic field in the other direction, which means we're going to induce a current in the other direction to oppose this change. We went from no current to some current, which meant we went from no magnetic field to some magnetic field, which meant we went from no flux to some flux. We want to oppose that change. We induce a magnetic field the other way. We generate current going the other way. Now, this current won't completely go backwards. It's not like it could generate, it's not going to induce a current stronger than that change. At most, it'll completely cancel, but usually it'll just reduce it somewhat. But this is kind of an important thing. This means that a solenoid, when you put it in a circuit, the benefit to this is a solenoid will resist large changes in current. So a solenoid resists large changes in current. And so this is beneficial in a circuit because you can imagine many situations where maybe you have a really high spike in current and you don't want that very high spike in current. You want that to be a smoother thing so that things can actually react to it appropriately and things don't burn out. A solenoid is used for that. Once we start talking about currents that actually alternate with time, AC currents, solenoids are going to be very important in that because they allow you to control high frequency changes. If your current's changing very quickly, a solenoid will kind of remove those high frequencies. So this is what we're going to be talking about for the rest of today. Solenoids, aka we call them inductors in circuits. Every inductor that you're going to see in a circuit element moving forward, so if you're doing electrical engineering or anything else with circuits, they're just going to be called inductors, and they're basically just solenoids. This is the basic setup, which is just going to outline exactly what I already talked about. So when we close switch 1, that's the exact problem that I just showed here. When you close switch 1, we're going from no current. So we start with current equals 0 to current equals V over R. That's what it immediately wants to do. But the inductor will oppose change in current. So we went from no current to some current. The inductor is going to oppose that. Mason asked, is there a difference between inductance and self-inductance? Yes, because there's something called mutual inductance. So just moving forward, I'm just going to pretty much say inductance, and that's self-inductance. In future classes, though, you may see mutual inductance, but we're not worried about that in our class. So when I say inductance, it's self-inductance, but there is another version that we're not talking about in this class. Okay, so switch 1 closes, and we get that opposing current, and that is, I use the word charging. This it's kind of like RC circuits, if you remember back when we covered those. We closed our circuit and the capacitor charged. We can kind of think of this similarly, where we see that the current will exponentially increase. Sorry, this is not exponentially increase, but it's kind of, it tapers off. So it's not, I'm going to correct this from exponentially, because exponentially means it would go sharply upwards. So current will increase as seen here. So initially it's going to have the largest opposition to the current, and then it's going to kind of take longer and longer and longer, and we get this flat line. Eventually it reaches the maximum. What is the maximum? The maximum is as if the inductor wasn't there. Basically, it's going to get to a point where you see here, the rate of change of current, di dt, is the slope. If I have current here on the left and I have time here on the bottom, di dt is literally a slope. So you see here the slope actually gets smaller and smaller and smaller until it's 0. Once the current's no longer changing, the inductor doesn't care. The inductor is just going to act like a resistor, basically. The inductor only cares, it cares the most at kind of this beginning thing. That's when the slope's going to be the highest, and then it kind of tapers off. And I'm not going to go through the derivation. We're not going to worry about that, but this is the equation for it. The current with respect to time in a circuit with a resistor and an inductor is the voltage of the battery. That's what that EMF is. Voltage of battery divided by the resistance in the circuit times parentheses 1 minus e to the negative resistance times time over L. So if you want to figure out the current 3 seconds after, you just plug in 3, plug in all your values, and you're going to get the current. We have a time constant for this. This is tau. This is called the time constant. Before we had our RC time constant. This is our RL time constant. And it's just L over R. It literally was just a substitution. You see here tau. You see here L and R. So tau equals L over R. Just a simple substitution. That's all we did here. We just defined this variable. If we want to look at the voltage drop across the inductor, so as time goes on, the inductor is going to have some voltage drop across it. And that is just given by this nice little slope down here, where the voltage drop is going to decrease because the current's going to decrease. Okay? So the current increases with time, but the voltage drop across it decreases with time, and that is actually because, and I'll write this down here, the voltage drop across an inductor equals the inductance times di dt. So let me go ahead and write that in this slide here. EMF equals negative L di dt. So the derivation to get from current to this is you just take the derivative of this with respect to time, and you return epsilon times e to the negative t over tau. And you can see here why this makes sense then. As the change in current with respect to time decreases, and this is absolute value. That's why it's not a negative, absolute value. So Devin asked, so resistors resist voltage and solenoids resist current. No, resistors resist current. Inductors, aka in this case solenoids, inductors resist change in current. So resistors resist current. Inductors resist a change in current. Inductors don't care how much current there is, they care how quickly the current is changing. And we can see that here. Inductors care about the rate of change of current. Okay, so I'm going to give you all a couple seconds to kind of digest some of this. If you want to kind of look at the future slides, you're welcome to. But we'll spend just a couple minutes and we'll reconvene at 11:50. If you have any questions about the test or anything else, or anything we've covered, feel free to ask it in chat and I'll answer it now. And then after the break, we'll go ahead and finish up the last few slides. And let's see. You can see the dog again, because that's more enjoyable than seeing my face. Yep. And there we go. L is the inductance. Correct. Yeah, and dog's name is Buster. If there's been one benefit to this unfortunate coronavirus time, it is that animals have been getting more time with their owners than ever before. Yep, so Bonzi asked, so as current passes through an inductor, all that happens is that the change in current goes down. An inductor, if the current is constant, inductors literally just act as a wire. They don't care if the current is constant, they just act like a wire. But when the current is changing, say it's increasing or decreasing, whether that's fast or slow, an inductor will oppose that change. The faster the change is, the more it opposes it. We see here that's where that the voltage drop across an inductor, and this is kind of like how much it's opposing it, is going to be based on that rate of change and the inductance. If you have a bigger solenoid, if you have a solenoid with a bigger inductance, you're going to have a higher opposition to it. And initially, all of the voltage drop, the second you switch it, all the voltage drop is across the inductance. The inductor completely opposes it, but then it isn't able to oppose it as time goes on. So, all right. So we're going to go ahead and continue on. So this was the case of, I used the word charging. This is the case of switch 1 being closed, where we are running the current through that. And now at some time, as some time has passed, this thing is just going to act like a wire. Once enough time passes, current's just going to flow and everything's going to be great. Current is going to flow through here when the switch 1 is closed. And it'll reach a constant and it'll act just like a wire. Okay. So, one thing I want to draw a parallel to, because we talked about, remember, RC circuits, so this is where we're going backwards. This is if you have a resistor and a capacitor. And this was, so if we imagine closing switch A here, that's just like closing switch 1 before. The capacitor actually had the opposite effect, where current was maximum with respect to time, and you actually got a current that went like this. It went down. And so, this actually behaves exactly opposite to inductors. So capacitors and inductors behave opposite to each other. Capacitors initially don't oppose the current, because the reason they oppose current is as time goes on, charge gets built up here. The more charge that gets built up, the more voltage this gets, and it opposes the current because this builds up and you can't put any more positive charge at some point. But initially, there's no charge on it. So at some point later, you build up charge, but initially there isn't any, so it's maximum. At some time later, this thing is completely charged and no longer can you put charge in there. If you can't put charge in there, current goes to 0. So that's what this graph here shows. This was the review for RC circuits. You see here it starts at the maximum current and then it goes down. So this is kind of interesting because inductors and capacitors are kind of opposites to each other. Inductors don't like large changes in currents, and capacitors don't like current going in one direction for a long time. So inductors don't like large changes in current. Capacitors don't really care about large change in current. Inductors, after a long time has passed, they don't really do anything anymore. Whereas capacitors, after a long time has passed, they completely stop it. So inductors stop it all at the beginning. Capacitors stop it all at the end. Inductors, at a long time, don't do anything. Capacitors at the very beginning, So basically just inverse. So capacitors initially don't care, inductors care a lot. At the end, capacitors really care, inductors don't care. So that's just kind of a useful thing. So functionally, you can imagine if you built a circuit, depending on what effect you'd want, depends on whether you want to put an inductor or capacitor. Okay. How long? Okay, so I'll quickly do this example problem. The question here is, how long after switch 1 is thrown does it take for the current to reach half its maximum value? So I have my current with respect to time equals epsilon over r. I'm just writing the equation for negative t r over L. Okay, all I did here was I literally wrote the equation that I have here. The current with respect to time. If I want to figure how long it takes for current to reach a value, I'm going to use the equation for current with respect to time. Okay, one substitution I'm going to make here is remember that epsilon over r is the maximum current because epsilon equals IR. The maximum current is just going to be the voltage of the battery divided by the resistance, because that means the inductor doesn't matter anymore. So epsilon equals I max times R. You get maximum current when the resistor has all of the voltage drop across it. Okay, so I max 1 minus e to the negative t R over L. So the question is, how long does it take for the current to reach half its maximum value? So what is I of t going to be? Well, it's going to be I max divided by 2. At some time, the current has reached its half of its maximum value. So that's what this problem is saying. When it half its maximum value, well, that means this is half of its maximum value. So all I did was I changed from this to this, and I of t is that. So we can see here the I maxes actually end up canceling. So you just get 1/2 equals 1 minus e to the negative t R over L. So I get of 1/2 equals T times R over L negative. And you get here that T equals negative L over R ln of 1/2. Now, you may be wondering, isn't this a problem because I have a negative sign? Ln of 1/2 is a negative number. So the negatives end up canceling, so you get a positive time. So the thought process here is that I of t equals I max over 2. I mean, this is the idea here. We just need to figure out what the question is asking. How long does it take to reach half its maximum value? Well, how long does it take is just going to be when this equals the maximum current divided by 2, and I just rewrote epsilon over r as I max. That's the only change there. And then you just solve for t. How long does it take to reach this value? How much time has to pass to reach I max over 2? So this is a really easy problem, and this is actually a good review for RC circuits, because this is a similar problem I could ask for an RC circuit, which is something that'd be on the test. Is I say, how long would it take to reach a current that is 1/3 the maximum value? And instead of using this equation, you would use the one for an RC circuit, which is seen here. So if that's the case, just a reminder that I max equals VB over R. Same exact substitution. So it's an easy problem I could ask. Okay, so the next thing is I'm just asking you to literally solve for the current. So using the same equation, using the current with respect to time equals I max. Well, I'm actually going to put the epsilon over r here because you're going to need that. Epsilon over r, 1 minus e to the negative t r over L. What is the current 2 milliseconds after the switch is closed? This is just plug and chug. I gave you R, I gave you L, I gave you time, I gave you the voltage on the battery. It's 12 volts. Plug and chug, find the value. So that's 2 milliseconds, and then the next one is what happens 2 seconds after the switch is closed. And the thing with these problems is this to give you a sense of how long it takes for this inductor to stop carrying anymore. So that's kind of a hint for the second one that the current's going to be very low. Okay. Now here's the interesting thing, just like with the capacitor. So I'm going to quickly jump up to the example problem I gave here. When it was charging, the current went down with respect to time, but the second you switch this switch to B, the capacitor is fully charged and will actually discharge. So when I go to B, it'll actually discharge and current will then flow the other way. Inductors will do the same thing. An inductor, where did the negative come from? I'll quickly answer that in just a second, Hannah. When I have my inductor, so here was my circuit. We had the battery, we had a switch, and the switch could go one of two ways. Could go this way, so we have our inductor. I'll draw a better inductor there. And this should have a resistor. Okay, so here's our two circuits. So either you close it. When it's closed this way, that is charging. And I'm using the word charging very loosely here. I'm not putting charge on it, but I am just like, we're going to use that terminology. And when the switch is here, we'll call that discharging. So the idea behind this one is a little bit more, a little bit different. So the capacitor, it made sense. You put charge on it. Once you stop putting the battery there, it ends up discharging because the charge is no longer held here. What happens in this case with the inductor is the second I make my circuit look like this, where the battery is removed, what now happens is originally, okay, the battery was pushing current through. The battery was causing current to happen. The second you close this, there's no longer any current flowing. Well, the inductor was happy with current flowing. The inductor was like, yeah, I want this current to be flowing. So the inductor will actually keep pushing current through this to try to keep, to keep magnetic flux constant. inductor will generate current. So this is the opposite of that. In the first case, it went from no current to some current. Now when you flip it, it went from some current to no current, and it's going to oppose that change. So it will actually generate current in the same way. It won't do it forever. Now drops with time. Before it increased with time. Now it drops with respect to time. And our voltage is the same thing. That equation doesn't change because our thing starts with the maximum voltage and then decreases. The other one was the same way. And it's same with the derivative. So basically just remember these equations and remember the idea that an inductor will actually try to keep current, will try to oppose a change, whether that change is an increase in current or a decrease. All right, and Hannah asked, where did the negative come from for the e to the TR over L? So this is the equation here, and my apologies, this should be a negative. I just forgot to write the negative there. The original equation, so it's epsilon over r times 1 minus e to the negative TR over L. So I just forgot to write that one, but I wrote it in all the other ones because it should be there. And that comes from our original equation here. The negative RT over L. Okay. So this is the idea, and to help provide a visualization of this, I have this link here, which you can kind of view in your own time, but I'll quickly open up. This shows, it's kind of in fast forward, what happens if you actually put an inductor and a capacitor together, and there was no resistor here. The capacitor, and again, unfortunately, it's way too quick, and I don't think I can slow it down, but the capacitor gets a charge. So it builds up the charge, and then it's like, okay, I don't want the charge anymore, so it'll release it. So the resistor and the inductor just oppose each other. Remember I said they act in opposites? This is a visualization of that. Unfortunately, it's super quick, but I just wanted to kind of show that this idea that you can have a resistor and capacitor, and you get this kind of oscillating thing going on here. Because they act opposite to each other, when the inductor is happy, the capacitor is not happy. When the capacitor is happy, the inductor is not happy. So you get this back and forth of current. And if there's no resistance, then this will just continue to happen forever. This back and forth. So that one didn't necessarily relate, but this is just LC circuit. This is the most I'm going to talk about this. I don't have any questions I'm asking about it, but it's just to kind of, again, show this idea of oscillating. So quick recap, and an inductor and a circuit together. Here we go. We're going to jump up here. When you put a resistor and an inductor and a circuit together, initially, when you close it, the inductor is going to oppose the change in current because it goes from no current to some current. It opposes that change until eventually it kind of just acts like a wire. So it opposes and then it stops carrying as much. Okay, once that's fully done, if we then open this switch and we close switch 2, the inductor no longer has the battery pushing that current through it. So now the circuit naturally wants to go from some current to no current. Well, the inductor doesn't like that change, so it tries to keep the current the same, but the resistor saps that energy away, and so the current steadily decreases. What's the difference between RC circuits and DC circuits? An RC circuit is a DC circuit. The reason I call it an RC circuit is because it just has a resistor and a capacitor. So these circuits, these RC circuits, these RL circuits, for right now, they're all direct current circuits. DC means direct current. That means current is going in one way. It's a constant source. The battery is a constant source of voltage. But it's a specific kind of DC circuit where you have a resistor and a capacitor, hence the R and the EC. And an LR circuit is a DC circuit that just has an inductor, which is L, and a resistor, which is R. Oh, and yeah, this is back. This is a typo, which unfortunately somehow existed. This should be current will decrease, as you can see in the graph. Decrease, and this one is exponentially. exponent. All right, great. Okay, so that's it. We're done with inductors. So that is everything there. Again, after the test, make certain you do the. So there will be a quiz for this one. This is the very last thing I'm going to quickly highlight. So we do have a quiz for inductors, but that quiz should be set. And if not, I may need to update the deadline for that. Inductors and RC circuits is not due until a long time from now, April 17th. So you have lots of time. So you have all this time to study for that test. And then you'll have a full week. You'll have 2 weeks to get ready for that test. Because we also have to talk about our RLC circuits. So we're going to talk about RLC circuits from the 6th to the 10th. And the next quiz will cover both inductors and those. And RLC circuits will be AC circuits. So we'll get to that though. But that's it. All right. You all have a great rest of the day. Yes, and I'm going to move the physics I care about too. I will do that now so I don't forget. But you all should see that change soon. And I'm going to go ahead and start up the stream for the clicker questions from last class as well. So, oh, and Daz asked for a quick repeat, so I'll spend 2 seconds doing that. When I close switch 2, the inductor keeps current the same. So when I close switch 2, the current's basically going to flow around, but it's going to decrease with respect to time. So it's going to just get smaller and smaller and smaller and smaller. So you close switch 2, and then this is going to start to generate a current. But that current will decrease with time as seen here. So the inductor will be the one driving it, but it can't do it forever. Okay. And the test questions are roughly the same difficulty as the quizzes. They should match that. All right. Have a great rest of the day. I will see you at the clicker question stream if you're there. If not, have a great weekend. And I will see you all on Monday for the review. See you then.